Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 7, Lesson 5, during which we are going to talk about nuclear reactions. So let's use this brilliant technique that I call reading all the words. Nuclear, something having to do with the nucleus. And then reaction. We are using the word reaction here just like we use the word reaction in chemistry. So as you might remember, a chemical reaction is when we take different compounds like C3H8. Maybe you remember that. That's called a hydrocarbon because it's a molecule made of only the elements hydrogen and carbon. And I can combine this hydrocarbon, C3H8, with oxygen. Now, when I combine something with oxygen, that's called a combustion reaction. This is just to remind you of what chemical reactions are from chemistry. Don't worry if some of this vocabulary doesn't sound familiar to you. But it's true that when a hydrocarbon combines with oxygen, we call that the combustion of a hydrocarbon. And it's a really special kind of chemical reaction because the products, the stuff on the right, are always carbon dioxide, CO2, and water, H2O. So what's here at the beginning? Carbon, hydrogen, and oxygen. What's here at the end? Carbon, hydrogen, and oxygen. So we haven't introduced any new kinds of atoms, which is good. But also, one of the rules of chemical reactions is that every atom that's there at the beginning is still there at the end. And every atom that's there at the end is there because it was there at the beginning. So you might be saying, but wait, there's 3 atoms of carbon at the beginning, and there's only 1 atom of carbon at the end. That's right. That's why I have to put a 3 here. That's called a coefficient. And so I have 3 molecules of CO2. I have COO and another COO and another COO. And then you might say, but there's 8 atoms of hydrogen and there's only 2 atoms of hydrogen at the end. That's why I'm going to put a 4 here. So I've got HHO, 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 and HHO, 4 of them. And then, so I've got 3 carbons at the beginning, 3 carbons at the end, 8 hydrogens at the beginning, 8 hydrogens at the end. How many oxygens do I have at the end? 4 there, and 1, 2, 3, 4, 5, 6 there. So I've got 10 oxygens at the end, meaning I need 10, 5 times 2 is 10, oxygens at the beginning. Now, I hope that all felt familiar to you, because when you take physics, it's usually because you've taken chemistry beforehand. So what we did is we balanced our reaction. We balanced our equation with all the atoms that are there on the left equal all the atoms that are there on the right. Before atoms, after atoms, all the same. So that's what we mean when we say reactions. And we're going to be doing some reactions in this section where we have a little arrow in the beginning and we say stuff turns into other stuff. So we could call these things reactants and products. Often in our nuclear reactions, we talk about our parent nuclei, the nuclei that are there at the beginning, and then we talk about our product nuclei. I've only heard, I don't know why we don't call them parent and child nuclei. I have heard them called daughter nuclei, but that's very gender specific, and I don't want to go there right now. So we'll just, our beginning nuclei and our resulting nuclei would probably be a better way of naming that. Right, our original nuclei and our final nuclei. All right, so let's remember that. I don't like crossing out the word parents. If you have parents at home, they're delightful people, and we appreciate them in so many ways, but we don't need that word here. All right, so let's talk about, I'm going to show you an example of a nuclear reaction, and then I'm going to talk about the principles that the example demonstrates. So uranium. Uranium is element number 92. And so if you look on the periodic table, not the decimal number, but the integer number in the box for uranium, letter U, is 92. And we often write that here on the bottom left. It's like a subscript, but it's on the left. But if you look at the decimal number, if you round it, is somewhere in the 230s. So when I call this uranium and the 92, that's redundant. If there's 92 protons, it's uranium. If it's uranium, there's 92 protons. So sometimes the 92 is left off. But the name of this thing that I just drew is called uranium-238. What does that look like? There's a nucleus, which contains how many protons? 92. But that nucleus also contains neutrons, and the protons and the neutrons are all mashed in there together. So what I have is a nucleus which contains protons and neutrons. Protons and neutrons. This NEU at the beginning of neutrons has to do with neutral, no charge. Whereas the nucleus has a charge. The nucleus is positive. So this nu doesn't mean neutral. So NU without the E. So how many things do I have here in this nucleus? Well, I've got the number of protons plus the number of neutrons is the total number of things. This number up here is the number of things in the nucleus. It's the number of protons plus the number of neutrons. And protons and neutrons are called nucleons. Not in EU nucleons, but in U nucleons, having to do with the nucleus. Protons live in the nucleus. Therefore, protons are called nucleons. Neutrons live in the nucleus. Therefore, neutrons are nucleons. There are two kinds of nucleons, protons and neutrons. So this, I could call it the nucleon number, but no one calls it that. I would call it that, but no one else does. This is called the mass number. It's the number of things in the nucleus. Protons and neutrons have slightly different, but very close to the same mass. And then this is called the atomic number. The mass number is abbreviated with the letter capital A. The atomic number, which you might think should be A, but it's not, the atomic number is abbreviated with a capital Z. So there we go. Uranium-238 has 92 protons. How many neutrons does it have? Well, there are 238 nucleons. So from that 238, I'm going to subtract 92, and I get 146. So there's 146 neutrons. 92 protons, 146 neutrons, which gives me a total of 238 nucleons. The number of protons plus the number of neutrons equals the number of nucleons. But usually we do this subtraction problem because usually the number of nucleons and the number of protons is given. Sometimes the number of protons is not given, but if I call it uranium-238, then the 92 is given because I can look at the periodic table and see the 92 there. All right, a lot of chemistry review there. Now, uranium-238 often undergoes what we call alpha decay. It undergoes alpha decay. What that means is this emits an alpha particle. An alpha particle, so now we have to define that, an alpha particle. There's the Greek letter alpha. An alpha particle is 2 protons and 2 neutrons stuck together. That's all it is. We named it an alpha particle when these things were happening. Yeah, our species, knew that these things were flying around. And we did not yet know what they were made of. So they called it an alpha particle. And then it turned out later on, they figured out, oh, it's just 2 protons and 2 neutrons. Now, if we were to add to that some electrons, 2 protons, 2 electrons, oh, it's helium. So this is a helium atom. A helium atom is not an alpha particle. If I rip the electrons off, get rid of those electrons, and I just have this, that's an alpha particle. So an alpha particle is a helium nucleus. 2 protons, 2 neutrons. So sometimes a uranium nucleus will emit, it will shoot out a helium nucleus. Helium has atomic number Z2. How many protons? 2. How many neutrons? 2. How many nucleons? 4. And remember, it's the nucleon number or the mass that goes up there. So He42. Now, when the uranium-238 emits a helium nucleus, an alpha particle, the question is, what's left? So sometimes we'll say, well, there's something we don't know, X. What is X? Well, now we're going to go back to this example I showed you right here. In a reaction, all the stuff that's there at the beginning, all the protons, neutrons, electrons, everything that's there at the beginning is still there at the end. So we had a mass of 238 at the beginning. We need to have a mass of 238 at the end. 4 plus 234 is 238. Now, these 92 protons, we think of this as the charge. Protons have a charge of +1. So there's 2 protons there. There must be 90 protons there. And so what I do is I draw these, they're kind of like circles, but they're not. They're long and wide. I draw this, I circle here. This is my conservation of charge. All these numbers on the right have to add up to the numbers on the left. And then I draw another similar shape here. This is called conservation of mass. 234 plus 4 is 238. So when we're doing these reactions, we have to conserve charge by making sure that the bottom numbers on the right add up to the bottom numbers on the left, and we have to conserve mass. Now, the other word I haven't talked about yet is nuclear. This happens in the nucleus, and I've tried to call this not an atom, but I've tried to call it, I've tried not to use a word for that yet. But really, this is a uranium nucleus that's going to turn into this helium nucleus and this other nucleus. Now, X, maybe we don't know that identity, but we can figure out that identity if we look at our periodic table, because we know that there's 90 protons. So if there's 90 protons, we can look at our periodic table here and we look for 90. Where is there a 90? Do you see it down there? TH, is that thorium? So it's TH. So then if that were what we were wondering about, I could say X is TH. And we found what it turned into. X is TH. All right, let me give you a couple more examples and see if that illuminates what I'm trying to show you here. There's another kind of nuclear reaction. We talked about alpha decay, when a thing gives off an alpha particle and turns into something else. Maybe I didn't use the word decay. Sometimes this is called alpha emission, but sometimes it's called alpha decay because this thing naturally turns into this thing. So we use the word decay, you know, I'm aging, I'm decaying, it happens naturally. So there we go. There's another kind of decay called beta decay. And so that is the emission of a beta particle, which it turns out, we didn't know when we named it that. We are species, not me. But it turns out that a beta decay is just an electron. You might have a question. If you've got a question about me saying an electron in a nuclear reaction, that's a good question. I'll get to it. Press pause and write your question down if you have a question about emitting an electron in a nuclear reaction. But let's talk about it right now, beta decay. So have you heard of carbon-14? Have you? Let's take a quick peek at that periodic table. Again, really fast. Carbon is here. Carbon has an atomic number 6. So Z equals 6, meaning there are 6 protons. And then this mass number is really close to 12. It says 12.011, meaning the majority of the carbon in the world, in the universe, has a mass of 12. But this specific carbon nucleus has a mass of 14. Now, sometimes we say carbon-14 and we write it like that. And I can put the 6 here. The 6 is optional because to be carbon is to have 6 protons. So the 6 really is redundant. Either way, it's carbon-14. What does a carbon nucleus have? It has 1, 2, 3, 4, 5, 6 protons. And then if it's carbon-14, 6 plus 8 is 14. So there's 1, 2, 3, 4, 5, 6, 7, 8 neutrons. 6 and 8 is 14. So there are 14 things in here. There are 14 nucleons, hence carbon-14. Well, what will happen to carbon-14? I've told you carbon-14 sometimes emits a beta particle. So I could write a little, a beta there. And a beta particle, it turns out, has a charge of -1. And we're going to call it a mass of 0. And then, so instead of beta, what thing has a charge of -1 and a mass of 0? Well, that's an electron. Let me rewrite that so it looks a little prettier. E, 0, -1. And what's going to be left over after that happens? Well, I need a charge of 6. What plus -1 is 6? 7. And I need a mass of 14. 0 plus what is 14? 14. And then we go back to our periodic table. And if you look at the periodic table, the thing with 7 protons is, I'm going to check and just make sure. I think it's nitrogen, capital N, but I'm just going to check and make sure I've got it right. Yes. And then I'm actually going to show you because it's fun to see that here. There's nitrogen. And you'll see not only does nitrogen have a charge of 7 protons, but it has a mass of 14. So that's the way nitrogen usually is. And because that's the way it usually is, we're going to say that is stable. Carbon usually has 12 nucleons for a total of 6 protons and 6 neutrons. That would have been stable. But by putting those extra 2 neutrons in there, that made it unstable. So it would decay and turn into this nitrogen nucleus. And oh my goodness, an electron popped out. Now, your question earlier might have been, wait a minute, I thought this was a nuclear reaction. I thought we started out with a nucleus and we got a new nucleus. We do. How did a nucleus emit an electron? Because what's in the nucleus? What are the nucleons in the nucleus? Protons and neutrons. Well, so how could, there's protons and neutrons in there, and it shot out an electron. This drove me crazy when I was in high school. How can a nucleus shoot out an electron? What? No electrons in there. So let me show you another nuclear reaction. It turns out that a neutron can decay into other things. A neutron. The thing that goes on the top is the mass. What's the mass of a neutron? 1. The thing that goes on the bottom is the charge. What's the charge of a neutron? 0. Okay. And so this neutron, right? Because there were 6 protons. Now there's 7 protons. Where'd that extra proton come from? There were 14 nucleons. There's still 14 nucleons, but I gained a proton. So one of these neutrons must have disappeared. So you're telling me that a neutron is going to turn into a proton. How did I figure that out? I had 14 nucleons. I've still got 14 nucleons. 6 of them were protons, meaning 8 were neutrons. Now 7 of them are protons. I gained a proton. And oh, there's only 7 left. Instead of 8 neutrons, now there's only 7. So you're telling me a neutron is turning into a proton. Proton still has a mass of 1, but this proton has a charge of +1. Okay, now let's see what else is going to have to be here. If I'm going to conserve mass on the top, 1 equals 1 plus 0. If I'm going to conserve charge, 0 is 1 plus -1. What thing has a mass of 0 and a charge of -1? An electron. So this is telling me that in some nuclear reactions, like this one, a neutron is turning into a proton and an electron. And that is how out of this nucleus, the neutron turns into a proton. And when it does that, it ejects an electron. And then even more so, this nitrogen, if it's going to be an atom, it needs to have 1 more electron, right? How many electrons are in a carbon atom? 6. How many electrons are in a nitrogen atom? 7. Where does this electron go? It goes out and becomes part of the electron cloud of the nitrogen atom. But this is what happened in the nucleus. The neutron turned into a proton and shot out an electron. Weirdest thing in the world for an electron to come shooting out of a nucleus where there aren't any electrons. So some of these nuclear reactions are kind of cool. One of the things that we looked at way earlier in the year, we talked about neutrons and protons and their masses. Look at this. Proton mass, 1.67265 times 10 to the minus 27th kilograms. We could just call that 1.7 times 10 to the minus 27th kilograms. Neutron mass, 1.67495 times 10 to the minus 27. Well, we could just call that 1.7. We usually say protons and neutrons have about the same mass. 1.675, 1.673. Neutrons actually have a slightly larger mass than protons. Oh, it's important that neutrons have a slightly larger mass than protons, because this electron, which we say has a mass of 0, well, we know it's not really 0. We know electrons have a mass of 9.11 times 10 to the minus 31 kilograms. 1.675 times 10 to the minus 27th kilograms. 1.673 times 10 to the minus 27th kilograms. Oh, so it's important that this mass is a little less than this, so this works out. In fact, if you were to add these two together, you would still get slightly less mass than this. So, these are our estimates where we conserve mass, conservation of mass up here. The 0 is 1 plus 0 plus 1 is 1. But these two numbers don't quite add up to this. So if you were to take this mass and subtract from it this sum, there's still some mass that disappeared. Remember this equation? The mass that disappeared times 9 times 10 to the 16th would tell you how much energy also is released. Well, that's certainly fun. Remember this being our rest energy. Remember we called that rest energy in a previous video. All right. I'm just going to peek at my clock. Oh, I'm almost done. All right. There's one vocabulary word that I did not mention, and I had a note to myself to be sure that I mentioned it. Isotope. I told you that sometimes a carbon atom has 12 nucleons, and sometimes a carbon atom has 14 nucleons. So if you counted, I've got 6 neutrons here, I've got 8 neutrons here. I made 6 little black dots, I made 8 little black dots. Both of them have 6 protons. So 6 protons means it's carbon. 6 protons means it's carbon. 12 nucleons means it's carbon 12. 14 nucleons means it's carbon 14. We have different isotopes of carbon. The word isotopes is used in this sentence. We have different kinds of carbon. So isotope is a word that can be used in place of the word kind. We have different types of carbon. So if you think of tope as the word type, and iso meaning same, I think iso is a prefix that means the same. So what's the same about them? One has 12, one has 14. They're both carbon. So it's the same element with different masses. So it's the same type. There's different kinds or different types of carbon. Isotope. So those are the two most common isotopes, types of carbon. Variations, varieties. Hydrogen is fun. Some hydrogen atoms have a proton and an electron. Some hydrogen atoms, in addition to the proton and electron, have 1 neutron. And some hydrogen atoms, in addition to the proton and the electron, have 2 neutrons. So this is called hydrogen. This is called hydrogen. This is called hydrogen. They're all hydrogen. And they all have a charge of 1 because they all have 1 proton. But this one has 1 nucleon. This one has 2 nucleons. This one has 3 nucleons. Isn't that fun? There's 3 different kinds or 3 isotopes. Isotope. I-S-O-T-O-P-E-S. It's hard to write and talk at the same time. 3 isotopes of hydrogen. 3 isotopes of hydrogen. This one is called hydrogen. It's the most common one. This one is called deuterium. This one is called tritium. Deuterium, like duo. Tritium for try. So those are just fun things to talk about, different kinds of hydrogen. How do I know that this is the most common one? if I look at the periodic table at hydrogen, this says 1.0080. It's actually 1 point out to more decimal places, 1.00794. But anyway, regardless, who cares? That's really close to 1. This mass of 1 means most hydrogen has a mass of 1. What we do to find that number is we do a weighted average. We do this mass 1 times the percent of hydrogen atoms that have this, plus this mass 2 times the percent of atoms that are like this, plus this mass 3 times the percent of atoms that are like this. And since that weighted average gives us something very close to 1, that's how I know that most hydrogen atoms are like this. All right, well, that was some fun chemistry review and a little bit of math and some pretty pictures. Nice variety in there for you. Thank you for joining me for our talk today about nuclear reactions. I hope you have a wonderful day, but whatever you do, don't break the laws of physics.